For almost 20 years, physics lived with a problem it couldn't escape. The atom, the supposed basic unit of matter, simply did not add up. Physicists recalculated, rewrote theories, checked experiments, and always hit the same wall. Atomic nuclei had too much mass and too much positive charge at the same time. It was as if the heart of the atom was hiding something invisible, something that broke the rules of matter itself. Some believed the problem was unsolvable. Others suspected a missing particle, unseen, uncharged, undetected. No tracks, no signal in any detector, just a hole in the model. Into that fog of uncertainty stepped one quiet, stubborn physicist at Cambridge, James Chadwick. What he uncovered didn't just solve a puzzle. It rewrote our understanding of the atom, opened the door to nuclear energy, and changed the course of the 20th century. Today, you'll discover how the neutron was revealed, the missing piece of the atom. How a chain of misunderstood experiments led to one of the most important discoveries in physics. Let's begin. In the early 1900s, it looked like the atom was a finished story. Ernest Rutherford had fired alpha particles at thin gold foil and watched a few of them bounce almost straight back, as if they'd hit something dense and solid hidden inside the atom. From this, he concluded that almost all the mass and all the positive charge of an atom are packed into a tiny, central nucleus with electrons orbiting around it like planets around a star. Science celebrated this picture. Textbooks were written with pride. Students memorized that elegant structure with confidence. Then Niels Bohr came along and added quantum rules to those orbits. Suddenly, the periodic table, spectral lines, and chemical behavior all seemed to fall into place. For a moment, the atom looked elegant, complete, and under control. But beneath that elegance, something was very wrong. Physicists knew simple facts like these. Hydrogen's nucleus has charge +1 and mass of 1 atomic mass unit. Helium's nucleus has charge +2 and mass of 4 atomic mass units. That suggested a straightforward pattern. Heavier nuclei might just be made of many protons packed together, with some electrons inside the nucleus to reduce the overall charge to the correct value. So for nitrogen 1,4, the story went like this: 14 protons in the nucleus, 7 nuclear electrons trapped inside, net charge, +7. Matches nitrogen. Mass, 14, since electrons are very light. A neat trick. Too neat. As the 1910s and 1920s went on, the cracks began to appear. Isotopes were the first big warning sign. Chemists like Frederick Soddy discovered that the same element could exist in multiple forms with identical chemical behavior but different masses, like chlorine 3,5 and chlorine 3,7. Or several isotopes of uranium. If nuclei were just protons plus nuclear electrons, why would two atoms with the same number of protons have different masses? You could try to fix it by hiding more electrons in the nucleus, but that only made the model more artificial and unstable. And then came quantum mechanics. Quantum theory took one look at a nucleus crammed full of electrons and said, "No way." Electrons, confined to such a tiny region, should, by the uncertainty principle, have enormous kinetic energies. They wouldn't sit still and behave nicely. The nucleus would be a raging storm of high-energy electrons, nothing like what experiments suggested. Worse, the model gave the wrong answers for spin and magnetic moments of many nuclei. Nitrogen 1,4 in the proton plus nuclear electrons picture should have had half-integer spin. But experiments showed it behaved like a particle with integer spin. The numbers didn't just fail, they clashed head-on with reality. The protons plus nuclear electrons nucleus looked like a house built on shifting sand. Every calculation exposed a flaw. Every new measurement threatened the fragile model. Physicists could feel it. The nucleus was hiding a missing piece. A neutral, invisible something that carried mass but no charge, and that nobody had ever seen. The The first person to really say it out loud was Rutherford himself. In 1920, during his famous Bakerian lecture on the nuclear constitution of atoms, Rutherford proposed something bold. Maybe the nucleus contained not only protons and electrons, but a new kind of neutral particle. He imagined it as a sort of neutral doublet, a proton with charge +1 and an electron with charge 1, bound together so tightly that to the outside world they behaved like a single neutral object. This hypothetical particle would have almost the same mass as a proton, carry no net charge, and be able to slip between protons in the nucleus without causing electrical repulsion. In other words, it was the perfect building block to explain nuclear masses and isotopes. With this neutral particle, you could add mass to the nucleus without changing its charge, build heavier nuclei as combinations of protons and these neutral units, and match the observed atomic numbers and masses much more naturally. He even used the word neutron for this neutral nuclear component, though in his version it was still a proton-electron composite, not a truly fundamental particle. But there was a problem. No experiment had ever seen anything like it, no track in a cloud chamber, no deflection in electric or magnetic fields, nothing. And quantum theory hated the idea of squeezing an electron down into the volume of a proton. It violated the rules of relativity and spin in all the wrong ways. Rutherford's neutron remained for over a decade in a kind of scientific limbo, beautiful on paper, uncomfortable in the equations, and invisible in the lab. A tantalizing ghost of a particle waiting for evidence. It would take more than a decade and a long chain of clever experiments and honest misinterpretations before that shadowy idea turned into a real particle. Fast forward to 1930. In Gießen, Germany, Walther Bothe and Herbert Becker were running what seemed like a simple, routine nuclear experiment. They had a strong polonium source firing out alpha particles, and in front of it, they placed thin targets made of light elements: lithium, boron, and especially beryllium. When those alpha particles slammed into the light nuclei, something unexpected happened. A new kind of neutral radiation appeared. It was unlike anything they had seen before. They quickly noticed a few crucial facts. It wasn't deflected by electric or magnetic fields, so it carried no charge. It passed through thick layers of material much more easily than any known gamma rays. And when the target was beryllium, the effect became particularly strong and intense. Given the tools and theory of the time, Bothe and Becker made the most reasonable guess they could. This had to be extremely high-energy gamma radiation, a new kind of artificial gamma ray produced when alpha particles struck light nuclei like beryllium. The physics community went along with that explanation. Gamma rays were already known to be very penetrating, so super gamma rays sounded exotic, but not impossible. What no one realized was that they were staring straight at the first clear appearance of Rutherford's mysterious neutral particle. They had seen the neutron, they just didn't know it yet. 2 years later, in Paris, the super gamma ray story began to crack. Irène Joliot-Curie and Frédéric Joliot-Curie set out to examine this mysterious neutral radiation in more detail. They placed blocks of paraffin wax and other hydrogen-rich materials in the path of the beam produced by alpha particles hitting beryllium, and then carefully measured what happened. Paraffin is loaded with hydrogen atoms, which means it's loaded with protons. What they saw was shocking. The neutral radiation was smashing protons out of the paraffin at very high energies, far higher than protons normally receive from ordinary gamma rays. These recoil protons left unmistakable tracks in detectors and cloud chambers. The Joliot-Curies tried to make sense of this, using the familiar Compton effect, where gamma rays scatter off electrons and transfer some of their energy and momentum. They kept the same idea, but in their equations, they simply swapped electrons for protons. That's when the math went crazy. To give protons that much energy, the gamma rays would have to be insanely energetic, far beyond anything any known radioactive source could produce. Something clearly didn't add up. On the one hand, the radiation behaved like gamma rays in some basic ways. It was neutral and very penetrating. On the other hand, the energy it was dumping into protons was way too large to be explained by any plausible gamma ray energy. The Joliot-Curies still tried to hold onto the gamma ray explanation because, honestly, what else could it be? But the tension was obvious. The experiments were shouting that the picture was wrong. Their setup had pulled back the curtain. They just hadn't yet recognized what was standing behind it. Back in Cambridge, at the Cavendish Laboratory, James Chadwick was paying very close attention. The Cavendish at that time was a compact powerhouse of physics. Cloud chambers humming, counters ticking, radioactive sources carefully stored in drawers, and bold new ideas floating through the corridors. The air was full of metal, chalk dust, and unresolved questions. Chadwick had worked side by side with Rutherford, shared his obsession with the nucleus, and had built a reputation as an expert in detecting the faintest traces of nuclear radiation. When he heard about the Paris results, about neutral radiation knocking protons out of paraffin with impossibly high energies, he immediately grew suspicious of the gamma ray explanation. To him, the logic was brutal and simple. If this really were gamma radiation, the photons would need absurdly high energies. So maybe it isn't gamma radiation. Chadwick remembered Rutherford's old idea, a massive neutral particle living inside the nucleus. Suddenly, the mysterious beam from beryllium looked like the perfect candidate. Yes, it was neutral, which explains why electric and magnetic fields couldn't deflect it. It was highly penetrating. Unlike charged particles, it wouldn't be slowed down easily, and it could hit protons hard, so it had to carry significant mass, comparable to the proton. If those gamma rays were actually neutral particles with nearly the mass of a proton, then everything the Joliot-Curies had seen started to make sense. Chadwick decided he wasn't going to just speculate. He was going to prove it. In late 1931 and early 1932, he began the series of experiments that would finally bring the neutron out of hiding. Chadwick's setup was conceptually simple and devastatingly effective. He used a polonium source that emitted alpha particles. He fired those alphas at a beryllium target, recreating the Botha-Becker experiment and producing the same mysterious neutral radiation. In front of this radiation, he placed a block of paraffin wax, packed with hydrogen and therefore packed with protons. Behind the paraffin, he set up detectors, ionization chambers, and counters to measure the energies of the protons that were knocked out. But Chadwick didn't stop at paraffin. He also let the neutral radiation pass through gases like nitrogen, helium, and argon, and carefully measured how much energy their nuclei picked up, how strongly they recoiled. Every recoil was a data point. Every kicked nucleus was a clue. Using the conservation of energy and momentum, Chadwick worked backwards. If this radiation were gamma photons, what photon energies would be needed to produce the observed proton recoils? If instead it were massive neutral particles, what mass would those particles need to have? For gamma rays, the answer was ridiculous. The photons would need energies far beyond anything that polonium-beryllium reactions could realistically produce. The gamma ray hypothesis collapsed under its own numbers. For massive particles, the story suddenly made sense. The best fit was unmistakable. The neutral particle had a mass very close to that of the proton, about 1 atomic mass unit. It wasn't light. It wasn't a high-energy photon. It was something with mass and no charge. Exactly the kind of particle Rutherford had imagined back in 1920. But now, it wasn't just an idea. It was supported by hard experimental data. In February 1932, Chadwick sent a short paper to Nature titled Possible Existence of a Neutron. In it, He calmly laid out his reasoning and calculations, concluding the evidence is in favor of the view that the radiation consists of particles of mass approximately equal to that of the proton and zero charge. Within a few months, he followed up with a longer, more detailed paper, The Existence of a Neutron, giving a full description of the experiments and the measured properties of this new particle. The neutron was no longer a shadow in Rutherford's lecture. It was real, measured, quantified, named. In 1935, James Chadwick was awarded the Nobel Prize in Physics for the discovery of the neutron. From that moment on, nuclear physics would never be the same. The moment the neutron entered the picture, the old nuclear model collapsed like a bad prop on a stage. No more nuclear electrons. No more desperate attempts to cram electrons into a tiny nuclear core where quantum mechanics clearly didn't want them. Instead, the nucleus could finally be described in a simple, elegant way. Nucleus equals protons plus neutrons. Protons, charge plus 1, and mass. Neutrons, zero charge, similar mass, adding mass and stability. With that single idea, several long-standing problems practically solved themselves. First, isotopes finally made sense. Before the neutron, isotopes were a headache. Why would two atoms behave chemically the same, yet have different masses? With neutrons, the answer became almost embarrassingly simple. All atoms of the same element have the same number of protons, same charge, same chemistry. But their number of neutrons can change. Same element, different mass. So for carbon, for example. Carbon 1, 2, 6 protons plus 6 neutrons. Carbon-14, 6 protons plus 8 neutrons. Same element, same chemistry, different mass. That's it. Overnight, the periodic table didn't just look organized by charge. It clicked into a deeper order, built from protons and neutrons working together at the heart of every atom. Second, the nuclear spin and magnetic moments. The old nuclear electron model completely failed when it came to spin and magnetic moments. Take nitrogen 1,4 as an example. Experiments showed that its nucleus behaved like a particle with integer spin. But in the old picture, 14 protons plus 7 nuclear electrons, the math gave the wrong statistics. Quantum mechanics and experiment simply did not match. With neutrons, the problem disappeared. You no longer needed any electrons hiding inside the nucleus. Nuclear spin and magnetic properties could now be understood as the combined result of protons and neutrons, each with their own spin, arranged in specific configurations. Suddenly, quantum mechanics and nuclear measurements stopped arguing and started agreeing. Third, nuclear stability. In a protons-only nucleus, there's a big problem. All those positive charges are busy repelling each other. Coulomb repulsion is constantly trying to blow the nucleus apart. Neutrons fix that too. They add attractive nuclear force without adding any charge. Help glue protons together via the strong nuclear interaction. Allow each element to form stable combinations of protons and neutrons. If there are too few neutrons, the nucleus often becomes unstable and can undergo beta decay. If there are too many neutrons, it also becomes unstable. But within a certain range, just the right mix of protons and neutrons, nuclei become stable. What once looked like a chaotic bundle of positive charges turned into a well-structured system governed by clear rules. The impact of all this was enormous. Chadwick's neutron wasn't just one more particle added to the list. It was the piece that made the entire nuclear puzzle finally fall into place. The story could have ended there, with a neat fix to atomic theory. But the neutron was not just a missing puzzle piece. It turned out to be a key. Because neutrons have no electric charge, they can slip into nuclei far more easily than protons or alpha particles, which are strongly repelled by the positive charge of the nucleus. Physicists quickly realized what that meant. Neutrons are perfect projectiles for exploring and transforming nuclei. Chadwick's colleague Norman Feather soon used neutrons to smash into nitrogen nuclei, breaking them apart and observing reactions that produced new elements and particles. In Italy, Enrico Fermi and his team began bombarding many different elements with neutrons. They discovered new radioactive isotopes and showed that slow neutrons are especially effective at triggering nuclear reactions. Those experiments would later become crucial for the development of nuclear reactors. Then, in late 1938, a dramatic discovery in Berlin pushed everything into a new era. While bombarding uranium with neutrons, Otto Hahn and Fritz Strassmann found that the uranium nucleus sometimes split into two roughly equal pieces. Lighter elements like barium and krypton. Lise Meitner and Otto Frisch realized what this meant. This was nuclear fission, the uranium nucleus breaking apart and releasing an enormous amount of energy. And what triggered this fission? Neutrons. Even more powerful was the next realization. Fission itself can release more neutrons, and those neutrons can go on to cause further fissions. That means you can create a chain reaction. From there, the path led to nuclear reactors, turning the energy of fission into electricity. Nuclear weapons, focusing that same energy into devastating explosions. Medical radioisotopes and neutron scattering, giving us new tools to study and heal matter. All of that, the useful and the terrifying, traces back to a neutral particle that started as a theoretical fix for a mass problem inside the atom. The invisible brick that completed the nucleus became one of the central actors in human history. The neutron wasn't born from a single eureka moment. It emerged from a broken atomic model, awkward ideas about nuclear electrons, misread experiments with beryllium, and finally, one physicist brave enough to ask, what if this isn't light at all? James Chadwick turned a strange, ghost-like radiation into a new fundamental particle. That neutron fixed the structure of the atom, explained isotopes, resolved quantum contradictions, and opened the door to nuclear physics, nuclear energy, and nuclear weapons. The discovery of the neutron shows that science doesn't move in straight lines. It zigzags through mistakes, doubts, and paradoxes, but each wrong turn leaves a trace of truth behind. In 1932, the invisible became visible. For the first time, the atom finally made sense. If you enjoyed this journey into the heart of matter, don't forget to subscribe and keep exploring with us. The neutron is just the beginning.